All right, this is Saxon Advanced Math, lesson 87.A, and this is sum and difference identities. Now, a couple of things we need to talk about with identities. First of all, we have to remember what an identity is. An identity is something that equals itself always, right? We did this with like a conversion factor is an identity. It works out every time. Where x plus 2 equals 6 is not an identity. It's dependent upon the fact that only works when x is 4, right? So these are identities, and these are two new identities that we have. And the reason why we have to memorize, well, two, we actually have 6 here. The reason why these 6 identities become very, very important is because there's a little problem with algebra and working with trig that you can't just add them up. For instance, if I had the sine of 30 and the sine of 60, I can't say, well, that's the same as just saying sine 30 plus 60, so sine 90, right? And if I look at that doesn't work. Nor does it say, if I just add them up and say 1/2 plus root 3 over 2, that they don't equal, right? Because it should be, if I said 2 times the sine of 30, that should be the sine of 60, right? In our heads that makes sense, but two 30-degree angles don't have the same as 160 because 2 30s would be 2 times 1/2, right? 1/2 and 1/2 because that's the sine of 30. And that should give me 1 whole, right? But it doesn't. Its sine of 60 is actually root 3 over 2. So it's not perfect, right? And so when we're looking at this, we have a couple of identities that we are going to memorize, and by a couple I mean 6. And those identities sound horrible, but once you see them, they're really not that bad. And here's how they work. For the sine function, and then for the cosine, and these are review ones. So these are ones we already have memorized. For the sine, if we say the sine of a plus b, like this one, I'm saying that if I want to say sine 30 plus sine 30, right? Say sine of a plus b. It's the same as sine a cosine b plus cosine a sine b. Now, that sounds horrible, but stay with me here for just a moment because it gets easier. This is not that bad. When I do this, notice that my sine of a minus b is the same thing. Notice these are identical with the only difference being the negative. Okay, so that means if you memorize one, you can do the other, right? When they're added, they're added. When they're subtracted, they're subtracted. That's easy. Now that we go to the cosine functions, I say the cosine of a plus b. Well, it's a little different because now it goes cosine a, cosine b, sine a, sine b. And when you're adding, it's subtracting. So it's both are backwards, right? No longer a sine and cosine together. It's cosine, cosine, sine, sine, and you're subtracting for the cosine of a plus b. And then for d, for our fourth one here, a minus b, when you're subtracting, you're adding, and it's cosine, cosine, sine, sine. So these two are really similar. The only difference is it goes, on the sines, the positives stay with the positives. On the cosines, they're opposite. And on the sine functions, it's sine, cosine, right? And on the cosine, it's cosine, cosine, sine, sine. So if you can remember that that's how they work out, that's great. These are review. These are review. And on the review ones, I already know the tangent of theta equals the sine of the cosine. We've proved that in previous lessons. And we've proved that the sine squared theta plus cosine squared theta equals 1. Now, let's see where these are important and how these work in problems. Here I have example 87.1. And it says simplify the sine of theta plus 4. Now, in our algebra minds, we want to just distribute this and say, well, it's the same as sine of theta plus the sine of pi over 4. And it doesn't quite work that way. We have to use this identity right here. And the reason why we're using this identity is it is a function plus a function, right? It's a term plus a term. And so I'm going to use this equation, and I'll be able to put this up and say the sine of a and b. This is a, this is b. First and second, right? Sometimes we learn them that way with f's and s's. It doesn't really make a difference. This is my first and my second term. So I'm going to rewrite this as sine of theta, right? Cosine of the second one, theta, or pi over 4, plus the cosine of theta, sine of pi over 4. And this is just this formula rewritten for this example. Now I start breaking this down. Well, what is pi over 4? And I realize for those of you who think in radians very well, this is elementary and redundant, and how could you ever insult my intelligence? But for the rest of us mere mortals, we realize that degrees work out nicer in our head because we've learned in degrees first, not because they're easier. So when I do this, I say pi over 4. Well, pi is 180. 180 over 4 is 45. Oh, that's should spur your memory, a 45, 45, 90 triangle, right? And so I know on a 45, 45, 90 triangle that the sine of 45, opposite over hypotenuse, is 1 over root 2. And the cosine of 45 is, guess what? 1 over root 2, right? Because you have two sides the same. Doesn't really matter which one you're working with. Now, I'm going to then plug these in for the pi over 4. So the cosine of pi over 4 becomes 1 over root 2. The sine of pi over 4 becomes 1 over root 2. And they now have substituted in. Well, I don't really know what theta is, but I don't have to because I'm going to have a theta in my answer, and you'll see that. The next thing I did is I simplified this 1 over root 2. The only reason I'm doing that is it's not customary to leave a root 2 in the denominator. It's not customary to leave any roots in the denominator. So I go ahead and look at it and realize what would I multiply the top and the bottom by to get rid of that root? Well, root 2. So I multiply it by root 2 over root 2, and it becomes root 2 over 2, right? These times each other are 2. Root 2 times root 2 is 2, and 1 times root 2 is root 2. Now I substitute those in and get root 2 over 2 sine theta plus root 2 over 2 cosine theta. Well, where did those come from? That came from right up here where we just realized that now I'm going to put them out in front, right? I'm just moving them over and I'm simplifying them. Well, at this point, you should recognize that both of them have a root 2 over 2. So I could factor that out to the front and put it here. Now, this is an acceptable answer. I would certainly not mark that wrong because, hey, factoring at the end is not really a simplification step. But the book wants you to realize that I can make it into a much simpler format than this here. And that's what I've done. And we come up with an answer. Now, 87.2 is a little bit different. This is why trig identities came about, if you want to think of it that way. See, we are very spoiled as modern day technological users, and we have a very, very detailed sine, cosine, and tangent calculator at our fingertips. In fact, we have Siri or Google, and we just talk to it, and it tells us. If I said, hey, what's the sine of 45? I don't have to know a ratio for it in real life because I just look it up each time, right? But in history, when you were having to do this by hand, there was no real good way to have this table. So the ones that they'd already worked out, like our common triangles, like 30, 60, 90, and 45, 45, 90, those were ones that we already knew. So instead of saying, what is the cosine of 15, and coming up with that decimal, it was much, much more useful to say, could I rewrite 15 in a correlation to two triangles I already know, or two angles I already know? Well, yes, I can. I can rewrite it as 60 minus 45. Notice that 60 minus 45 is still 15. I know how to get 60 and I know how to get 45. I could do the same thing by saying 30 plus 15, but I don't know the 15. Right? So these are ones that I already know, and that's why we're using 60 and 45. Now, this example asks us, using this, find what the cosine of 15 is. So I'm going to rewrite it using this function and say cosine is 60 minus 45. Notice that now I have an A and a B. And I say cosine of 60 minus 45 equals, well, I need a cosine function, one subtraction, and I use this trig identity, cosine 60, or 45, sine 60, sine 45. Well, now I write my two special triangles, 1, 2, root 3, and 1, 1, root 2, and I start plugging these in. What's the cosine of 60? And I know we never thought we'd actually use them this much, but we do. And the cosine of 60 is 1 over 2. I plug that in. Then I move to the cosine of 45. Well, what's cosine of 45? Well, that would be adjacent over hypotenuse, 1 over root 2. Then I move to the next one, right? And I'm just moving right on down the line, sine of 60. For 60, sine 60 is opposite over hypotenuse, root 3 over 2. Then I move to the sine of 45, 1 over root 2, right? Which is either angle you want, they're both 45. At this point, I just go back to my algebra. So I multiply 1/2 times 1 over root 2 and get 1 over 2 root 2. Multiply root 3 over 2 times 1 over root 2 and get root 2 root 3 over root 2. I find a common denominator or simplify that by getting the roots out of the denominator by multiplying my root 2 over root 2, and that gives me 4 on the bottom here and 4 on the bottom here. And it gives me a root 2 and a root 6 up there. Okay, well, therefore I can say I have a common denominator and I add them, root of 2 plus a root of 6 over 4. And this we found without having to use a calculator or a table. This is the cosine of 15 right here without having to actually look it up or use the calculator to solve it. This is where the trig identities actually shine and why we do them. 87.3 asks us to simplify cosine of theta plus pi over 2. Now, this is, I really probably didn't have to do this example, but I'm going to go through it quickly. This is addition, so which one are we going to use? Addition of the cosine. We're going to use this one here, right? And I plugged them all in. I'm going through this quickly. The only thing I want you to notice is that when I do so, I realize that I'm going to have a unique situation because pi over 2 is 90 degrees, and we use cosine of 90 is 0, and that cancels the full first half of this. The sine of 90 is 1, that cancels out most of this one, and I'm left with just negative sine over, or negative sine of theta. This is a simplification problem more than a solve. And these are really simple once we realize what we're doing. We are using these trig identities to break down and to show different ways that I can work together with trig functions.